Tonight, we're going to shatter something you thought you understood: distance in space. You've heard the numbers: 4 light years to the nearest star, 2.5 million light years to Andromeda, 93 billion light years across the observable universe. You nod when you hear these figures. You think you grasp them. But here's the uncomfortable truth most people never confront. You don't. Your brain is physically incapable of truly comprehending what these distances mean. And the units we use to measure them, light years, parsecs, astronomical units, they weren't designed to help you understand. They were designed to make impossible numbers manageable. By the end of this journey, you'll realize that everything you thought you knew about distance in space was an illusion. The reality is far stranger. Before we dive in, if you find this kind of deep exploration fascinating, a quick like or subscribe would really help the channel grow. It's a small thing, but it means a lot. Now, get yourself comfortable. Let's begin. Let's start with something you know intimately: distance. You've been navigating it your entire life. The walk from your bedroom to the kitchen, the commute to work, the flight across the country to visit family. These are distances you comprehend because you've experienced them. You know what they feel like in your bones. You have reference points built from years of living in your body, moving through space, feeling time pass as you travel. When someone tells you a coffee shop is half a mile away, you don't need to calculate anything. Your brain instantly translates that into about a 10-minute walk. Maybe 15 if you're taking your time. When someone mentions a city is 300 miles distant, you think road trip. Maybe 5 hours of driving. You've done trips like that before. You understand what 300 miles means in terms of time, effort, fuel consumption, rest stops, and scenery passing by your window. This intuitive understanding of distance took millions of years of evolution to develop. Our ancestors needed to know how far the watering hole was, how far the hunting grounds extended, how far they could safely travel and still make it back before nightfall, how far a predator could chase them before giving up. Distance, for humans, has always been intimately connected to survival, to effort, to what our bodies could actually accomplish in the real world. And this is precisely why cosmic distances shatter us. When you hear that the nearest star to our sun, Proxima Centauri, is 4.24 light years away, something peculiar happens in your brain. You hear the number, you nod, you think you've processed the information. You might even repeat it to someone else later, feeling knowledgeable, but you haven't truly understood it. Not really. Your brain has simply filed it away as a big number, a label, without ever grasping what it actually represents. Here's why this matters more than you might think. A light year sounds like a unit of time. It has the word year right there in it. Your brain naturally, almost unavoidably, assumes it's measuring duration, like a fiscal year, like a calendar year, like the year you graduated or the year you got married. But a light year isn't a measure of time at all. It's a measure of distance. It's the distance that light travels in 1 year. And that distinction, which seems simple enough when stated plainly, creates a cascade of misunderstandings that affect everything we think we know about space. Light travels at approximately 186,000 miles per second. Let me say that again because the words might have slid past you. 186,000 miles. Every single second. That's roughly 300,000 kilometers per second if you prefer metric. This speed is so incomprehensibly fast that your brain cannot form a meaningful picture of it. In the time it takes you to blink, about 300 milliseconds, light has traveled roughly 56,000 miles. That's more than twice around Earth's equator. In one blink, by the time you finish reading this sentence, light has traveled far enough to circle our planet several times. It never stops. It never slows. It simply races through the void at this constant, unwavering velocity. Now multiply that speed by every second in a year. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. When you multiply all of that together, you get approximately 31,536,000 seconds in a year. Light travels 186,000 miles during every single one of those seconds. The result is what we call a light year. Approximately 5.88 trillion miles. That's a 5 followed by 12 zeros. When you write it out fully, it looks like this: 5,879,000,000,000 miles, give or take a few billion. We round because at these scales, a few billion miles is essentially a rounding error, and that's just one light year, a single unit in the astronomer's toolkit. Now, here's where the illusion takes hold. When I told you Proxima Centauri is 4.24 light years away, your brain tried to do something useful with that information. It attempted to relate this distance to something you understand. It reached for a reference point, but it failed, because there is nothing, absolutely nothing, in human experience that prepares you for a distance of 25 trillion miles. Your brain simply cannot construct a meaningful mental model of what that distance looks like, feels like, or means for anything practical. Think about the longest journey you've ever taken. Maybe you've flown across the Pacific Ocean. That's about 7,500 miles from Los Angeles to Sydney, Australia. A grueling flight. 15 hours or more in a metal tube, crossing an ocean so vast that for hours you see nothing but water in every direction. Maybe you've driven across the United States, coast to coast. That's roughly 2,800 miles from New York to Los Angeles, a journey that takes days of continuous driving, crossing mountains and deserts and plains, watching the landscape transform from forests to farmland to scrubland to coastline. These are long journeys by human standards. They require planning and resources and endurance. They test your patience. They make you tired. Now consider this. To travel from Earth to Proxima Centauri, you would need to make that cross-country drive approximately 8.9 billion times. Not 800, not 8,000, not 8 million. Nearly 9 billion trips across America, back to back, without ever stopping. If you drove across America once and then immediately turned around and drove back, and did that every single day for your entire life, and your children did the same, and their children, and so on for millions of generations, you still wouldn't come close to covering the distance to the nearest star. The number is so large it loses all meaning. It becomes noise, static. Just another big number that your brain files away in the same mental drawer where you keep other incomprehensible figures like the national debt or the number of grains of sand on Earth. You acknowledge it exists. You might even remember it. But you don't understand it. You can't. Your brain wasn't built for this. And here's the truly humbling part. Proxima Centauri is the closest star to our Sun. It's our nearest stellar neighbor, the absolute minimum distance to any other star in the entire universe. Everything else is further away. Most things in the cosmos are vastly, impossibly, incomprehensibly further away. This is what I mean when I say distance in space doesn't mean what you think it means. The numbers we use create an illusion of comprehension. You hear 4.24 light years and you think you understand. You nod. You file it away. But understanding implies the ability to truly grasp something, to hold it in your mind, to appreciate its implications, to feel its weight. And the human brain simply cannot do that with numbers this large. We've reached a scale where our cognitive machinery fails us completely. Let me try to illustrate this failure in another way. Imagine you're walking, a normal, comfortable pace, about 3 miles per hour. The kind of walk you might take through a park or around your neighborhood. How long would it take you to walk to Proxima Centauri? You might guess a long time. Thousands of years, maybe. Tens of thousands. The question itself seems almost absurd. But the actual answer is so extreme it transcends absurdity and enters a realm where numbers become meaningless sounds. At 3 miles per hour, walking 24 hours a day, every day, without ever stopping to eat or sleep or rest or tie your shoes, it would take you approximately 950 million years to reach Proxima Centauri. 950 million years. Let that number wash over you. That's longer than the entire age of complex multicellular life on Earth. The Cambrian explosion, when complex animal life first appeared in the fossil record, happened about 540 million years ago. Dinosaurs appeared about 230 million years ago and went extinct 66 million years ago. So you could go back in time to before the dinosaurs even existed, before the great reptiles had their first thought. Start walking toward Proxima Centauri, and you still wouldn't be there yet. You would still have hundreds of millions of years of walking ahead of you. Of course, nobody walks to stars. The very idea is laughable. So let's try something faster. The fastest humans have ever traveled was during the Apollo missions to the moon. Those astronauts, returning from lunar orbit, reached speeds of about 25,000 miles per hour relative to Earth. That's incredibly fast by any human standard. At that speed, you could fly from New York to Los Angeles in about 6 minutes. You could circle the entire Earth in roughly 1 hour. These astronauts were moving faster than any humans in history. So how long would it take to reach Proxima Centauri at Apollo speeds? The answer is approximately 113,000 years. Still an absurdly long time. Consider what 113,000 years means. All of recorded human history, every empire that rose and fell, every pharaoh and emperor and king, every discovery and invention, every war and peace, every generation that lived and loved and died, all of that spans only about 5,000 years. Maybe 10,000 if you're generous with your definition of recorded history. To reach the nearest star at Apollo speeds, you would need to repeat all of human civilization 22 times, end to end, one after another. If the ancient Sumerians, the first people to develop writing, had launched a spacecraft toward Proxima Centauri at Apollo speeds 5,000 years ago, that spacecraft would have traveled less than 5% of the distance by now. It would still have over 100,000 years of travel remaining. Your great-great-great-grandchildren, 100 generations hence, would still be waiting for it to arrive. And they would be waiting for a long, long time after that. What about faster spacecraft? What about the fastest thing humans have ever built? The Parker Solar Probe holds that record. When it swings close to the sun on its elliptical orbit, using our star's immense gravity to slingshot itself to incredible speeds, it reaches approximately 430,000 miles per hour. That's about 119 miles per second, nearly 20 times faster than the Apollo missions. Surely that helps close the gap. At Parker Solar Probe speeds, the journey to Proxima Centauri would take about 6,300 years. Better, certainly, but still longer than recorded civilization. If the ancient Egyptians had launched the Parker Solar Probe toward Proxima Centauri when they were stacking the first stones of the Great Pyramid at Giza, that probe still wouldn't have arrived yet. It would still be out there, still traveling, still have centuries to go before reaching our nearest stellar neighbor. And remember, we're still just talking about the closest star, one star out of hundreds of billions. The Milky Way galaxy contains somewhere between 200 billion and 400 billion stars. The exact number is uncertain because counting stars in a galaxy you're inside of is extraordinarily difficult. It's like trying to count all the trees in a forest while standing in the middle of it. You can see some clearly, but most are hidden behind others, obscured by dust and distance and the sheer overwhelming numbers. The vast majority of these stars are tens of thousands of light years away from us. Our Sun sits in a relatively sparse region of the galaxy, about 26,000 light years from the galactic center. The galaxy itself is roughly 100,000 light years across, a vast pinwheel of stars and gas and dust spinning slowly through the cosmic void. At Parker Solar Probe speeds, it would take approximately 170 million years just to cross our own galaxy from one side to the other. That's longer than the dinosaurs existed. Longer than mammals have been the dominant life form on Earth. You could start your journey when the first dinosaurs appeared and still not reach the other side of the Milky Way. This is what happens when you truly engage with cosmic distances, rather than simply hearing numbers and nodding politely. The scale is not just large, it's not just bigger than what we're used to. It's fundamentally, categorically different from anything humans evolved to comprehend. Our brains developed to understand distances we might actually need to travel in a lifetime. Distances that mattered for survival. A few miles to the nearest water source. A few dozen miles to follow migrating herds. Maybe a few hundred miles for the most ambitious journeys of ancient exploration. But cosmic distances exist on a completely different plane of reality. They're not just bigger versions of earthly distances, the way a mountain is a bigger version of a hill. They're something else entirely. They operate under rules our intuition cannot grasp, at scales our minds cannot picture, across spans of time that make human civilization look like a brief flicker. Here's another way to see this fundamental disconnect. Light is the fastest thing in the universe. Nothing can travel faster than light. This isn't merely a technological limitation that we haven't overcome yet, like the sound barrier was before Chuck Yeager broke it. It's not a challenge waiting for better engineering. It's a fundamental law of physics, woven into the very fabric of space-time itself. Albert Einstein showed us this over a century ago. The speed of light isn't just fast, it's the cosmic speed limit, the universe's maximum velocity. No amount of technological advancement will ever allow anything with mass to reach or exceed light speed. You could have infinite energy. You could have propulsion systems that would seem like magic to us today. You could have 1,000,000 years to work on the problem. It wouldn't matter. The speed of light is as immutable and absolute as the law of gravity. It's built into the structure of reality. And yet, even at this ultimate speed, the maximum velocity permitted by the laws of physics, it still takes 4.24 years for light to travel from Proxima Centauri to Earth. Think about what that means. The fastest possible thing in the universe, the upper limit of speed itself, still requires over 4 years to make the journey. When you look at Proxima Centauri through a telescope tonight, you're not seeing the star as it currently exists. You're seeing light that left that star more than 4 years ago. You're looking into the past. The star you observe is not the star as it exists at this precise moment. It's the star as it was years ago. If something dramatic happened to Proxima Centauri right now, if it suddenly flared or dimmed or exploded, you wouldn't know for over 4 years. The news would travel at light speed, and light speed, fast as it is, still takes time. Look at Sirius, the brightest star in the night sky, and you're seeing light from 8.6 years ago. Look at Vega, that brilliant blue-white star overhead in summer, and you're seeing light from 25 years in the past. Each star is a different window into a different moment in history. This hints at something profound that we'll explore later. Distance in space is inseparable from time. The further away something is, the deeper into history you're seeing. When you look at the Andromeda galaxy, you're seeing light that left 2.5 million years ago, before humans existed. And Andromeda is close. Most galaxies are billions of light years away. When we observe them, we're looking at the ancient past. The very concept of now becomes uncertain when you're dealing with cosmic distances. This is the first illusion we need to shatter completely. The comfortable belief that we understand cosmic distances because we can recite the numbers. We don't understand them. We can't. The numbers are just symbols, convenient shorthand for something our brains were never designed and never evolved to grasp. They're like words in a language we can pronounce but cannot comprehend. We can say 4.24 light years as easily as we can say 5 miles. But the two phrases represent distances that differ by a factor of more than 5 trillion. They exist in completely different realms of reality. Until we confront this limitation, honestly, until we acknowledge that cosmic distances defeat our comprehension entirely, we cannot begin to appreciate what distance truly means in the context of the universe. We'll continue nodding at numbers without understanding. We'll continue thinking we grasp the cosmos when we've barely scratched the surface of our own ignorance. The cosmos is not a bigger version of Earth. It's not a larger territory that we might eventually explore with enough time and clever engineering. It's not an ocean waiting for better ships. It's something else entirely. Something that operates on scales that break our intuition, challenge our understanding of reality, and humble every assumption we bring to it. And we're just getting started. Because the units we use to measure these distances, the very tools we've developed to make sense of the cosmos, they come with their own hidden traps and misconceptions. They don't just fail to help us understand. In some ways, they actively deceive us. Let me show you what I mean. Let's talk about how we measure cosmic distances, because the units themselves are part of the problem. They were designed by scientists for scientists, created to make impossible numbers manageable for calculation purposes. But in doing so, they created something dangerous, a false sense of understanding that masks the true nature of what we're measuring. The very tools we use to quantify the cosmos have become instruments of self-deception. The most familiar unit is the light year. You've heard this term countless times in documentaries, in science fiction, in casual conversation about space. It rolls off the tongue easily. But as I mentioned earlier, the light year is deeply misleading in ways that most people never consider. The word year sits right there in the name. Your brain, which processes language automatically and unconsciously, latches onto that familiar word, year. You know what a year is. You've lived through dozens of them. You understand years. So when you hear light year, some part of your brain assumes this is a temporal measurement, a duration, an amount of time. People hear light year and unconsciously think of it in temporal terms. They imagine light traveling for a year, which is accurate as far as it goes. Light does travel for 1 year to cover a light year of distance. But the critical translation from that year of travel to the actual distance covered often fails to happen in people's minds. The name itself creates confusion that most people never even notice they're experiencing. A light year is not a measure of time. It's a measure of distance. Specifically, it's about 5.88 trillion miles. That's the distance light covers in 1 year of continuous travel at 186,000 miles per second. The year in light year refers to how the distance is calculated, not what kind of measurement it is. But that linguistic quirk has confused generations of people trying to understand cosmic scales. Scientists have another unit that's even more obscure to the general public, the parsec. If you've seen certain science fiction movies, you might have heard this term, sometimes used incorrectly as a unit of time rather than distance. A parsec is approximately 3.26 light years, or about 19 trillion miles. It's a larger unit than a light year, used when even light years produce unwieldy numbers. The name parsec comes from combining two words, parallax and arcsecond. This refers to the method astronomers use to measure stellar distances. As Earth orbits the Sun over the course of a year, nearby stars appear to shift slightly against the background of more distant stars. This apparent shift is called parallax. By measuring the angle of that shift in arcseconds, which are tiny fractions of a degree, astronomers can calculate how far away a star is. A star that shows 1 arcsecond of parallax is 1 parsec away. Parsecs are actually the preferred unit among professional astronomers because they relate directly to measurement techniques. When you do the math to determine stellar distances, parsecs emerge naturally from the calculations. For scientists working with these numbers every day, parsecs make more sense than light years. But for the general public, parsecs are even more alien and unhelpful than light years. At least a light year has that deceptive familiarity, that false sense of understanding created by the word year. You think you know what it means, even though you don't really. A parsec doesn't even offer that illusion. It's just a strange word that conveys nothing to anyone who isn't an astronomer. Then there's the astronomical unit, abbreviated AU. This is the average distance from Earth to the Sun, approximately 93 million miles or 150 million kilometers. This unit works well for describing distances within our solar system. Mercury is about 0.4 AU from the Sun. Mars is about 1.5 AU. Jupiter sits at roughly 5.2 AU. Neptune, the most distant major planet, orbits at about 30 AU from our star. The AU gives us a useful yardstick for planetary distances. You can say Neptune is 30 times farther from the Sun than Earth is, and that ratio makes sense. It's comprehensible. You can picture 30 Earths lined up between the Sun and Neptune. The Kuiper Belt, that ring of icy bodies beyond Neptune where Pluto resides, extends from roughly 30 AU to about 50 AU from the Sun. The Oort cloud, the vast spherical shell of icy objects that marks the outer boundary of our solar system, extends from perhaps 2,000 AU to as far as 100,000 AU from the Sun. Even at these extreme distances within our solar system, the AU remains somewhat useful. But astronomical units break down completely when you try to use them for interstellar distances. Proxima Centauri, our nearest stellar neighbor, is approximately 270,000 AU away. At that point, you're back to numbers so large they lose all meaning. The AU was designed for solar system scales, and it simply doesn't translate to stellar distances. The unit becomes as useless as measuring the distance to another continent in inches. Here's the fundamental problem with all these units. They were developed to make calculations easier, not to aid human comprehension. When an astronomer says a galaxy is 10 megaparsecs away, they can immediately plug that number into equations. They can calculate redshift relationships. They can determine recession velocities. They can estimate masses and luminosities. The units serve a mathematical function, and they serve it well. But they don't help you understand what 10 megaparsecs actually means. They don't bridge the gap between number and lived experience. They're abstractions built on top of abstractions, layers of mathematical convenience that take you further and further from genuine comprehension with each added layer. Consider how we usually try to make cosmic distances relatable to ordinary people. We use scale models. We create analogies. We say things like, if the sun were the size of a basketball, Earth would be a small bead about 86 feet away, and the nearest star would be another basketball more than 4,000 miles distant. These analogies help a little. They give your brain something concrete to latch onto. 4,000 miles is a distance you can almost imagine. It's roughly the distance from New York to London, or from Los Angeles to Tokyo. You've perhaps traveled distances like that. You have some experiential reference point. But here's the problem. These analogies also fail in subtle but important ways. When you hear that scale model analogy, you might think, okay, 4,000 miles. I can sort of picture that. It's far, but it's a number I can work with. But consider what we've done to create that analogy. We've shrunk the sun, which is 864,000 miles in diameter, down to about 9 inches. We've shrunk Earth, which is almost 8,000 miles in diameter, down to a tiny bead about 1 millimeter across. We've compressed our entire solar system into something that fits in a large room. And at that incredible level of compression, the nearest star is still 4,000 miles away. Now try to extend that analogy to the rest of the galaxy. Try to scale the entire Milky Way at that same ratio. Where would the galactic center be in this model? Where would the nearest spiral arm fall? Where would the edge of the galaxy be? Where would other galaxies appear? The analogy collapses. Your brain can handle Earth as a tiny bead and the nearest star as 4,000 miles away. That's already stretching your visualization capacity to its limits. But it cannot extend that model to include hundreds of billions of stars spread across 100,000 light years. The scale model that seemed to work for one comparison fails completely, catastrophically, when you try to use it for the larger picture. Let me try a different scale model that might help you see just how empty space truly is. If you drew the solar system to scale, with the sun represented as a small marble about 1 centimeter across, Earth would be a nearly invisible grain of sand about 1 meter away. Jupiter would be a small pebble about 5 meters distant. Neptune would be a speck roughly 30 meters away, the length of a basketball court. You'd need a large field just to show the major planets. And at that same scale, where the sun is a marble and Neptune is 30 meters away, the nearest star would be another marble sitting roughly 270 kilometers distant. That's about the distance from London to Paris, or from Los Angeles to Las Vegas. Your entire scale model of the solar system, spread across a basketball court, would be one tiny cluster, and you'd have to travel hundreds of kilometers to reach the next one. And yet, even the distance to the nearest star is nothing compared to the scale of the galaxy. All the planets, all the asteroids, all the comets, everything we've ever sent a spacecraft to explore, all of it exists in a tiny bubble of space that's cosmically insignificant. This is the fundamental challenge we face when trying to understand cosmic distances. Our brains can grasp ratios between things of similar scale. We can understand that one building is twice as tall as another. We can visualize that one country is 10 times larger than another. We can picture a lake that's 5 times wider than a different lake. These ratios make sense because they connect things that exist at roughly the same order of magnitude. But cosmic distances involve ratios between things of wildly, absurdly different scales. The distance from Earth to the Sun compared to the distance from Earth to Proxima Centauri is a ratio of about 270,000 to 1. The distance to Proxima Centauri compared to the diameter of the Milky Way is a ratio of about 24,000 to 1. The diameter of the Milky Way compared to the distance to the edge of the observable universe is a ratio of roughly 930,000 to 1. These ratios are so extreme that no single mental model can contain them. Every time you try to zoom out, every time you try to extend your understanding to the next level of scale, your brain's capacity for visualization fails. The model breaks. The analogy collapses. You're left with numbers that have no experiential anchor, no connection to anything you've ever seen or touched or traveled. Let me give you another example of how our units actively mislead us about cosmic distances. When you hear that the observable universe is 93 billion light years across, you might pause and do some quick mental math. The universe is about 13.8 billion years old. Light travels 1 light year per year, by definition. So shouldn't the observable universe be about 13.8 billion light years across, or maybe 27.6 billion if you're counting from one edge to the other through Earth? Where does 93 billion come from? That number seems wrong. It seems like the universe couldn't possibly be bigger than the distance light could have traveled since the beginning of time. This confusion is extremely common, and it arises from hidden complexity in how cosmic distances actually work. Complexity that our units fail to convey. The universe has been expanding ever since the Big Bang. Not just the stuff in the universe moving apart, but space itself stretching, growing, inflating. Light from distant galaxies has been traveling toward us for billions of years, but during all that time, the space it was traveling through has been stretching. The galaxies that emitted that light have been carried further and further away by the expansion of space. So while the light from a distant galaxy might have been traveling for 13 billion years, the galaxy that emitted it is now much more than 13 billion light years away. Space expanded while the light was in transit. The galaxy got further away during the journey. It's like walking towards someone on a moving sidewalk that's carrying them away from you. You're making progress, but they're also receding. The result is that objects whose light has been traveling for 13 billion years are now more than 46 billion light years away. The observable universe, the sphere centered on Earth from which light has had time to reach us, is 93 billion light years in diameter. Not because the universe is older than we thought, but because space expanded while the light was traveling. This is another way that distance in space doesn't mean what you think it means. Distance isn't static. It's not a fixed measurement like the distance between 2 points on a rigid surface. The distance between galaxies is actively changing, moment by moment, as space itself expands. Two galaxies that were neighbors in the early universe might now be separated by billions of light years, not because either of them moved through space, but because the space between them grew. This is incredibly counterintuitive. In everyday life, distance is simple and fixed. If I stand here and you stand there, the distance between us remains constant unless one of us moves. But in space, the very fabric of the universe is stretching. Galaxies are being carried apart by the expansion of space itself, like dots on the surface of a balloon that's being inflated. And this expansion is accelerating. Distant galaxies are receding from us faster and faster as time goes on, pushed apart by a mysterious force we call dark energy. What does this mean for our understanding of distance? It means that some galaxies are now so far away and receding so quickly that light from them will never reach us, ever. They have crossed what astronomers call the cosmic horizon. They are beyond the boundary of the observable universe forever. No matter how long we wait, no matter how advanced our technology becomes, no matter how powerful our telescopes grow, we will never see light from these galaxies because the space between us is expanding faster than light can cross it. The galaxies haven't exceeded the speed of light themselves. Nothing can do that. But they don't need to. Space itself is inflating, and that inflation isn't subject to the cosmic speed limit. Think carefully about what that means. There are galaxies out there, real galaxies with hundreds of billions of stars and possibly trillions of planets that we can never observe. They exist, they're as real as our own Milky Way, but they are forever beyond our reach, not because they're too far away in some simple geometric sense, but because the expansion of space has permanently, irrevocably separated us. The universe is larger than the observable universe. How much larger? We don't know. We can't know. It might be a few times larger. It might be infinitely larger. The portion we can see might be an infinitesimally small fraction of the whole. We are fundamentally limited to our observable bubble, our cosmic horizon, and what lies beyond it is unknowable by any means we can conceive. This is another layer of deception built into our units and our terminology. When you hear the phrase observable universe, you might assume it's synonymous with the universe. It sounds comprehensive. Observable universe sounds like it describes everything that exists, but it doesn't. It describes only the portion from which light has had time to reach us. The actual universe extends beyond it in every direction, filled with galaxies we can never see, stars we can never catalogue, planets we can never discover. The expansion of space has created a fundamental boundary that no technology can overcome. This isn't an engineering problem waiting for a clever solution. It's a feature of the universe itself, a limitation woven into the structure of space-time. Now, let's talk about another way our representations of cosmic distances mislead us: the problem of dimensions. When you see a map of the universe, or a diagram showing the relative positions of stars and galaxies, you're looking at a two-dimensional representation of a three-dimensional reality. Sometimes astronomers add depth cues or color coding to suggest the third dimension, but fundamentally, you're looking at a flat image, and this creates all sorts of false impressions. Stars that appear close together in the sky, stars that seem to neighbor each other in photographs and star charts, might actually be separated by vast distances in three-dimensional space. One might be 100 light-years away from Earth, while another is 1,000 light-years away. They appear side by side from our perspective, but if you could fly out to them, you'd find they're nowhere near each other in actual space. Constellations, those familiar patterns we've gazed at for thousands of years, are perfect examples of this illusion. The stars in a constellation have no real relationship to each other. They're not gravitationally connected. They're not at similar distances. They're not part of any physical structure. They just happen to line up from Earth's particular vantage point. The Big Dipper, for instance, contains stars ranging from about 58 light-years to 124 light-years from Earth. Some are more than twice as far as others. They only appear to form a pattern because we're seeing them projected onto an imaginary two-dimensional dome. Similarly, when you see illustrations of our solar system in textbooks and documentaries, the planets are usually shown much closer together than they actually are. This is necessary for practical reasons. If you drew the solar system to true scale on a page, the planets would be invisible dots separated by vast amounts of empty space. You'd need a piece of paper miles long to show everything at a scale where the planets were even visible. But this necessary compression creates a fundamentally false impression of what the solar system actually looks like. People imagine planets strung along like beads on a necklace, relatively close together, with perhaps some asteroids floating around between them. The reality is vastly emptier. Here's another common misconception that our visual representations reinforce. People often imagine space as being full of stuff. They picture asteroid fields like in the movies, dense with tumbling rocks, requiring skillful piloting to navigate. They imagine stars clustered together in great glowing swarms. They picture galaxies as crowded, packed places where matter is abundant. But space is mostly empty, overwhelmingly, staggeringly, incomprehensibly empty. The average density of matter in the universe is approximately 5 atoms per cubic meter. Let me put that in perspective. The best vacuum we can create in a laboratory on Earth contains trillions of particles per cubic meter. Space is orders of magnitude emptier than any vacuum humans have ever produced. If you could take a cubic meter of random intergalactic space and somehow contain it, you'd almost certainly find nothing in it at all. Not a single atom. The matter that does exist in the universe is concentrated into stars and planets, with some gas and dust scattered between them. But those objects are separated by vast empty gulfs that contain essentially nothing. The spaces between stars aren't filled with anything. They're just space, emptiness extending for trillions of miles in every direction. Even within our solar system, which feels relatively crowded compared to interstellar space, the emptiness is hard to overstate. The asteroid belt, which science fiction has trained us to imagine as a dense field of rocks, is actually so empty that spacecraft routinely fly through it without any special navigation. The asteroids are separated by millions of miles. If you were floating in the asteroid belt and looking around, you probably wouldn't see a single asteroid visible to the naked eye, just blackness in every direction. This emptiness is another form of distance that our intuitions completely fail to grasp. We're accustomed to environments where stuff is nearby, where the air is full of molecules that we breathe, where the ground is solid beneath our feet, where objects occupy space and we navigate between them. We've never experienced true emptiness. But in space, the norm is emptiness. Stars are incredibly rare phenomena, tiny points of matter separated by light years of void. Galaxies are islands in an ocean of nothingness. The distances between things are filled with precisely that. Nothing. No air, no dust, no particles. Just the vacuum of space-time stretching on and on. When astronauts look out the window of the International Space Station, they see Earth below and the blackness of space above. That blackness looks like a ceiling, a dark background against which stars and planets are projected, like a planetarium dome. But it's not a ceiling. It's not a backdrop. It's depth. Real depth. It extends for billions of light years in every direction, filled with almost nothing. The space between you and the nearest galaxy is not a backdrop in front of which things happen. It's a real physical expanse that exists, that contains almost no matter, that stretches further than light has traveled since the beginning of time. It's emptiness on a scale that defies imagination. This is what our units fail to convey. They give you numbers, clean and precise and scientific sounding. 4.24 light years, 2.5 million light years, 93 billion light years. The numbers seem concrete, solid, meaningful, but they don't give you the emptiness. They don't communicate the void. They don't convey that space is not just large, but also incredibly, terrifyingly, existentially empty. Let me try one more approach to illustrate how our units deceive us into thinking we understand things we don't. Imagine you're trying to describe the wealth of billionaires to someone who has never heard of money. You could say that a particular billionaire has $100 billion, but that number means nothing without context. It's just a sound, a collection of syllables representing a quantity that has no connection to anything this person understands. Now imagine you explain that the average person earns about $50,000 per year. Suddenly there's a reference point. The billionaire's wealth is 2 million times that annual salary. To earn what that billionaire has, an average worker would need to work for 2 million years, 40,000 lifetimes. Every human who ever lived, working their entire lives, still wouldn't accumulate that wealth. Now you have context. Now the number starts to mean something. It's still hard to truly comprehend what 2 million years of labor represents, but at least you have a framework for understanding the ratio. You can start to grasp the magnitude. Cosmic distances lack this framework entirely. When I tell you that Betelgeuse, that reddish star marking Orion's shoulder, is roughly 700 light years away, you don't have a reference point. When I mention that the Andromeda Galaxy is 2.5 million light years distant, you don't have an experiential anchor to connect that number to anything you've lived or felt or traveled. I could tell you that 2.5 million light years equals approximately 25 quintillion miles, but that number is equally meaningless. It's just more noise, more syllables, more digits without significance. I could tell you it would take the Voyager 1 spacecraft, currently the most distant human-made object, about 37 billion years to reach Andromeda at its current speed. But that number is also beyond comprehension. 37 billion years. The universe itself is only 13.8 billion years old. The number tells you that the journey is impossibly long, but it doesn't help you understand what impossible actually means in this context. The units don't help. They just repackage the incomprehensibility in different forms. Light years, parsecs, astronomical units, miles, kilometers, none of them bridge the gap between cosmic scale and human experience. They're tools for calculation. Optimized for equations and scientific papers, they are not tools for understanding, for building intuitive models, for truly grasping what it means to be separated by such distances. This is the second great illusion we need to confront and discard. The comfortable belief that because we have units of measurement, because we can quantify these distances with precise numbers that extend to many decimal places, we therefore understand them. We don't. The units are abstractions that serve mathematical purposes. They allow scientists to perform calculations, make predictions, design spacecraft trajectories. They allow astronomers to communicate with each other using shared standards. They serve essential functions in the scientific enterprise, but they cannot give you an intuitive grasp of what cosmic distance truly means. They cannot make you feel what it would be like to cross such distances, because such crossings are impossible. They cannot connect the numbers to anything in your experience, because nothing in your experience relates to such scales. And the implications of this failure of understanding are profound, because if we don't truly grasp the distances involved, we also don't understand what they mean for the possibilities we imagine. The possibility of interstellar exploration, the possibility of communication with other civilizations, the possibility of contact with alien life, the possibility of escape if something goes wrong with Earth. We don't understand what it really means to be separated by light years from everything else that exists. We don't understand the isolation that cosmic distance imposes on every world, every civilization, every form of life that might exist scattered across the vastness. The units have given us a false sense of mastery. We can put numbers on things, so we think we understand them. But understanding requires more than numbers. It requires connection to experience, to intuition, to felt reality. And at cosmic scales, that connection simply doesn't exist. The universe is not a place we can navigate using the same tools we use to navigate Earth. It operates on different rules, at different scales, across different kinds of distance than anything in human experience. And once you understand that the units we use are themselves part of the deception, a strange new picture begins to emerge. A picture where distance in space isn't just a barrier to travel that we might someday overcome with better technology. It's something more fundamental. A barrier woven into the fabric of reality itself. Because distance in space isn't just separation in miles or light years. It's separation in something else. Something that changes everything about how we should think about our place in the cosmos. Time. Here's something that will fundamentally change how you look at the night sky for the rest of your life. Every single star you see is a window into the past. The further away something is, the older the light you're seeing. This isn't poetic metaphor. It isn't a figure of speech designed to make astronomy sound romantic. It's literal physical reality, as concrete as the ground beneath your feet. And once you truly grasp this fact, it transforms the very meaning of distance in space into something far stranger and more profound than simple separation. When you look at the sun, you're not seeing it as it exists at this exact moment. You're seeing the sun as it was approximately 8 minutes and 20 seconds ago. That's how long it takes light to travel the 93 million miles from the sun's surface to your eye. If the sun suddenly vanished right now, blinked out of existence in this precise instant, we wouldn't know for over 8 minutes. We'd continue basking in its warmth, seeing its light streaming through our windows, completely unaware that it no longer existed. The information about its disappearance would be racing toward us at 186,000 miles per second, but it would still need those 8 minutes to arrive. This delay seems trivial for the sun. 8 minutes isn't long enough to matter in any practical sense. You don't plan your day around the 8-minute time lag between solar events and your perception of them. But as distances increase, so does the temporal displacement between reality and observation. And here's where our ordinary, everyday understanding of distance begins to break down entirely. Here's where space stops behaving like the space we know and becomes something alien. The moon is approximately 1.3 light seconds away from Earth. When you look up at the moon tonight, you're seeing it as it was just over a second ago. That's close enough to seem like the present moment for all practical purposes. The delay is imperceptible to human senses. But Mars, at its closest approach to Earth, is about 3 light minutes away. When you look at Mars through a telescope, you're seeing the red planet as it was 3 minutes in the past. If something dramatic happened on Mars right now, an enormous dust storm erupting, a meteorite impact, a volcanic explosion, you wouldn't know about it for 3 full minutes after it occurred. The event would happen, and then you'd sit in ignorance while light carrying news of that event raced across millions of miles of void toward you. This creates immediate practical challenges for space exploration that most people never consider. When NASA operates rovers on Mars, like Curiosity or Perseverance, there's a communication delay of between 4 and 24 minutes each way, depending on where Mars and Earth are in their respective orbits around the Sun. Sometimes we're on the same side of the Sun, relatively close. Sometimes we're on opposite sides, much further apart. This delay means you cannot drive a Mars rover in real time. You can't sit at a control panel on Earth, watch a live feed from the rover's cameras, and steer around obstacles as they appear. That's impossible. The physics won't allow it. Instead, every command has to be carefully planned and sent. Then you wait. Minutes pass before the rover even receives your instructions. The rover executes those instructions, and then more minutes pass before confirmation reaches Earth. What seems like it should be a simple drive across the Martian surface becomes a painstaking exercise in delayed communication, anticipating problems before they happen, and programming autonomous responses for situations you can't predict. Imagine trying to drive a car where your view of the road is delayed by 4 minutes, and your steering wheel commands don't take effect for another 4 minutes. That's what controlling Mars rovers is like. Every move must be planned in advance because real-time reactions are physically impossible. Now extend this concept to the outer solar system, where distances grow dramatically larger. Saturn, home of the remarkable Cassini mission that explored the ringed planet and its moons for 13 years, orbits at a distance that varies from about 67 to 90 light minutes from Earth, depending on our orbital positions. When Cassini was orbiting Saturn, capturing those breathtaking images of the rings and the mysterious moon Titan, every photograph it sent took over an hour to reach Earth. Every command that mission controllers wanted to send took over an hour to arrive at the spacecraft. Round-trip communication required nearly 2.5 hours. The spacecraft had to operate with significant autonomy because real-time control was simply not possible. If something went wrong, if an instrument malfunctioned or an unexpected situation arose, Cassini had to handle it on its own for hours before ground controllers could even know there was a problem, let alone send instructions on how to respond. The spacecraft was essentially alone out there, a robot operating by programmed instructions with periodic check-ins from home. But these are still tiny distances compared to interstellar space. Light travels across our entire solar system, from the Sun to the outer reaches of the Kuiper Belt, in a matter of hours. A message can reach Pluto in about 5 hours. That's inconvenient for spacecraft operations, but manageable. We can still have something resembling a conversation with our robotic explorers, even if each exchange takes the better part of a day. When you jump to stellar distances, however, time delays stop being measured in minutes or hours. They're measured in years, decades, centuries, millennia. The light from Alpha Centauri, the closest star system to our Sun, left those stars about 4.3 years ago. When you look at Alpha Centauri tonight, assuming you're in the southern hemisphere where it's visible, you're seeing light that began its journey when you were 4 years younger than you are right now. Think about where you were 4 years ago, what you were doing, who you were with, the concerns and hopes you had. All of that time has passed since that light departed Alpha Centauri and began its long journey across the interstellar void. But other familiar stars show us even deeper into the past. Sirius, the brightest star in Earth's night sky, is 8.6 light-years away. Its light shows you the star as it was when today's third graders were being born. Polaris, the North Star that has guided travelers for millennia, is about 430 light-years distant. The light reaching your eye tonight left that star when Galileo was first turning his telescope toward the heavens. And Betelgeuse, that distinctive red giant in Orion, is roughly 700 light-years away. Its light began traveling toward Earth during the medieval period, centuries before Columbus sailed. That light has been traveling ever since at the maximum speed the universe allows. It's been crossing trillions of miles of empty space, racing through the darkness between stars where nothing exists, no planets, no asteroids, no gas clouds, just emptiness extending in every direction. And tonight, after years or centuries of continuous travel, those photons finally reach your eye. They end their journey by triggering a chemical reaction in your retina, creating the electrical signal your brain interprets as a point of light in the night sky. This might seem like a curiosity, an interesting piece of astronomical trivia to share at parties, but the implications are profound and unsettling once you follow them to their logical conclusions. Because if distance equals time in this way, if looking far away always means looking back in time, then everything we see in space is a record of the past. The universe we observe is not the universe as it exists right now, at this present moment. It's a mosaic of different eras, a patchwork quilt where each piece shows us a different moment in cosmic history depending on how far away it is. When you look at the Andromeda Galaxy, our nearest large galactic neighbor, you're seeing light that left that galaxy 2.5 million years ago. Let the weight of that number settle over you. 2.5 million years. When that light began its journey, human ancestors were barely recognizable as the lineage that would eventually produce us. The genus Homo, the group that includes modern humans and our closest extinct relatives, didn't exist yet. Our ancestors were Australopithecus, small-brained bipedal apes just beginning to experiment with stone tools. Lions and saber-toothed cats roamed across Africa and Eurasia. Mastodons and giant ground sloths walked the earth. The ice ages that would shape the continents we know hadn't yet begun their cycles of advance and retreat. The light left Andromeda, and while it was traveling across the intergalactic void, everything changed on Earth. Hominids evolved larger brains. Homo erectus emerged and spread across Africa and Asia. Homo sapiens appeared roughly 300,000 years ago. We developed language, art, agriculture, civilization. Empires rose and fell. The pyramids were built. The Roman Empire conquered and collapsed. The Renaissance flowered. The Industrial Revolution transformed society. World wars were fought. Humans walked on the moon. The internet connected the world. Your parents were born, grew up, met each other. You were born, lived your life up to this exact moment. All of that happened while the light from Andromeda was still in transit. And tonight, 2.5 million years after it began its journey, that light finally enters your eye. But here's where things become truly strange. The Andromeda you see tonight is not the Andromeda that exists now. It cannot be. In the 2.5 million years it took that light to reach us, things have changed in that distant galaxy. Stars have been born from collapsing clouds of gas and dust. Other stars have exhausted their fuel and died, some quietly fading into white dwarfs, others exploding as supernovae. Perhaps civilizations have risen on planets orbiting some of those stars. Perhaps they flourished for millions of years. Perhaps they went extinct. Perhaps others arose to replace them. The galaxy itself has rotated through a significant portion of its spiral structure. The positions of individual stars have shifted. The Andromeda we observe, frozen in light that departed 2.5 million years ago, is fundamentally different from the Andromeda that exists at this very moment in real time. And here's the crucial point. We will never see that present-day Andromeda. We will always be looking at its past. Even if we built the most powerful telescope imaginable, even if we developed sensors of impossible sensitivity, we would still only see light that had traveled for 2.5 million years to reach us. The present moment Andromeda is forever hidden from us, separated not just by distance but by time itself. This phenomenon gets even more extreme when you look at distant galaxies far beyond our local neighborhood. The Hubble Space Telescope has captured images of galaxies more than 13 billion light-years away. That light has been traveling since just a few 100 million years after the Big Bang, when the universe was young and hot and filled with the raw materials that would eventually become everything we see today. When we look at these galaxies, we're seeing the universe in its infancy. The structures we observe are among the first galaxies ever to form. They're infant galaxies, still assembling themselves from smaller fragments, still forming their first generations of stars. But those galaxies no longer look anything like what we see in those ancient images. Over 13 billion years, they've evolved beyond recognition. They've merged with neighboring galaxies, combining and recombining into larger structures. Their original stars have long since burned out, replaced by new generations of stars incorporating heavier elements forged in the cores and explosions of earlier stellar generations. The galaxy shapes, the stellar populations, the chemical compositions, everything has changed. The galaxies we see in those Hubble images don't exist anymore, not in any form we would recognize. We're looking at ghosts, echoes, photographs of something that transformed billions of years ago into something entirely different. The objects in those images are as gone as the dinosaurs, as vanished as ancient Rome, as disappeared as the ancestors who first looked up at the stars and wondered what they were. The James Webb Space Telescope, launched in 2021, is pushing this temporal archaeology even further. It's detecting light from galaxies that formed even earlier, closer to the Big Bang itself. Some of these objects are so incredibly distant that the light from them has been traveling for more than 13.4 billion years. That's almost the entire age of the universe. We're looking at the cosmos as it was when it was just a few % of its current age, when everything was compressed into a smaller, denser, hotter state that we can barely imagine. And here's something that will truly bend your mind if you follow it carefully. The cosmic microwave background radiation, that faint glow that fills the entire sky in every direction, is light from even further back in time. It's light from approximately 380,000 years after the Big Bang, when the universe first cooled enough to become transparent, allowing light to travel freely through space for the first time. Before that epoch, the universe was so hot and dense that light couldn't travel far without being absorbed and re-emitted by the plasma that filled all of space. The universe was opaque, like trying to see through fog. But about 380,000 years after the Big Bang, the temperature dropped enough for electrons to combine with protons and form neutral hydrogen atoms. Suddenly, the universe became transparent and light could travel unimpeded. The light released at that moment, the first light that could travel freely through the cosmos, has been traveling ever since. It's been crossing the universe for over 13.7 billion years, and we can detect it today. When we observe the cosmic microwave background, we're seeing the oldest light in the universe, the most ancient photons that can possibly reach us. We're looking at the universe as it was just 380,000 years after its birth. But here's what's remarkable about the cosmic microwave background. It's not a single point in space that we're looking at. It surrounds us in every direction. No matter which way we point our instruments, we see this ancient light. It forms a spherical shell around us, showing us the same era, the same cosmic age of 380,000 years post-Big Bang in every direction we look. This means the universe we observe is structured in time, like the layers of an onion. Close to us, we see the recent past. Stars a few light years away show us a few years ago. Galaxies millions of light years away show us millions of years ago. Galaxies billions of light years away show us billions of years ago. And at the edge of the observable universe, at the cosmic microwave background, we see the beginning, the first moment when looking was even possible. This is what distance truly means in space. It doesn't just separate objects across three-dimensional space like points on a map. It separates them in time. And because the speed of light is finite, because information cannot travel faster than those 186,000 miles per second, no matter how hard you try. This temporal separation is absolute and unbreakable. There is no way to know what's happening right now at a distant galaxy. The very concept of now becomes meaningless, becomes undefined, becomes philosophically incoherent when you apply it across cosmic distances. Right now at Andromeda isn't a statement that has any real meaning. There is no cosmic present moment shared by Earth and Andromeda. There's just the light that left there and eventually arrives here, bringing news of the past. Think about what this means for the search for extraterrestrial intelligence, a question that has fascinated humanity for generations. If there's a civilization in the Andromeda galaxy, intelligent beings on a planet orbiting one of that galaxy's trillion stars, and if they have telescopes, and if right now they're pointing those telescopes at the Milky Way, what do they see? They don't see us. They can't. They're seeing our galaxy as it was 2.5 million years ago. They might see evidence of stars and planets. They might detect chemical signatures suggesting that life exists somewhere in the Milky Way, but they're not seeing human civilization. They're not detecting our radio transmissions or observing our city lights or picking up any sign that intelligent, technological beings live here, because 2.5 million years ago, we didn't exist. The most sophisticated life forms on Earth were apes that hadn't yet learned to make fire. Now imagine that civilization decides to send us a message. They encode information somehow, perhaps in radio waves or laser pulses, and they transmit it toward the Milky Way, toward where they believe interesting chemistry might be occurring. We wouldn't receive that message for 2.5 million years. By the time it arrived, humanity as we know it might be extinct. We might have evolved into something completely different, descendants that would barely recognize us as ancestors. We might have spread across the galaxy and transformed into a civilization spanning thousands of star systems. Or we might be gone entirely, replaced by whatever comes next on Earth, whether that's another intelligent species, artificial minds, or just the empty ruins of a technological civilization that burned too bright and flamed out. And if we did receive the message, if our descendants were still around and capable of understanding it, any response we sent would take another 2.5 million years to reach them. The entire exchange, from their first transmission to their receipt of our reply, would span 5 million years. An entire conversation consisting of exactly 2 messages would take longer than the existence of the genus Homo. Conversations at that pace can hardly be called conversations at all. They're more like messages in bottles thrown into an ocean of time, received by descendants so distant they're essentially different species, replied to by beings who won't hear the response for epochs. This is the profound isolation that cosmic distance imposes on every world, every civilization, every form of life that might exist anywhere in the universe. It's not just that other stars and galaxies are far away in space, like distant cities on a map that you could theoretically visit with enough time and resources. They're far away in time. Communication across cosmic distances isn't just slow in the way that mail was slower than telegraph and telegraph was slower than telephone. It operates across timescales that exceed the lifetime of civilizations, species, biological families, and sometimes even the stars themselves. There are galaxies so far away that light from them will never reach us. The expansion of space is accelerating, driven by dark energy, and some distant regions are receding from us faster than light can travel. This doesn't violate Einstein's relativity, because nothing is moving through space faster than light. The galaxies themselves are essentially stationary in their local space, but space itself is expanding, stretching faster than light can cross it. These regions are beyond our cosmic horizon. They have passed the point of no return. They will never be visible from Earth, not in 1 billion years, not in 1 trillion years, not ever. This means there are galaxies out there, real galaxies with hundreds of billions of stars and almost certainly trillions of planets that exist right now but will never be observable by anyone in our region of space. We can never see them. We can never know what's there. They are causally disconnected from us, separated by a boundary that no technology, no matter how advanced, can overcome. The universe is larger than the observable universe. How much larger? We don't know. We can't know. It might be a few times larger. It might be millions of times larger. It might be infinite, extending forever in every direction, containing an endless number of galaxies that will forever remain beyond our sight. The observable universe is like a sphere of visibility centered on Earth. We can see about 46 billion light years in every direction, the limit set by the age of the universe and the speed of light. But there's nothing special about Earth's position. Every point in the universe has its own observable sphere. Hypothetical beings on a planet at the edge of our observable universe would have their own observable universe, overlapping with ours but extending in different directions. They would see regions of space we can never see, and we would see regions they can never see. The universe is not one thing that can be seen in its entirety from any vantage point. It's divided into overlapping bubbles of observation, each centered on a different location, each fundamentally limited by the finite speed of light. This is what the speed of light creates: horizons of visibility, boundaries to knowledge, limits to understanding that are built into the very structure of space-time itself. These aren't limitations of our technology. They're not challenges waiting for some breakthrough that will sweep them aside. They're fundamental features of reality, as basic as the existence of space and time themselves. Distance in space isn't just a measurement you can read off a ruler or calculate with an equation. It's a boundary, a constraint, a fundamental limit on what can ever be known by any observer anywhere in the universe. And here's the unsettling implication of all this. If distance equals time, and if time creates insurmountable barriers to communication and observation, then the universe is not a connected whole in any meaningful sense. It's not one big place where everything coexists in a shared present moment. It's a collection of islands, separated by gulfs of time as much as by gulfs of space. Each island can see other islands, but only as they were in the past. The further away an island is, the deeper into history you see when you look at it. And the furthest islands are receding beyond reach forever, carried by the expansion of space beyond the cosmic horizon, lost to us for eternity. When you look up at the night sky on a clear evening, you're not seeing the universe as it is. You're seeing a kaleidoscope of different eras assembled into a single visual field. Each star is showing you its own unique window into the past. The closest stars show you a few years ago. Nearby galaxies show you millions of years ago. Distant galaxies show you billions of years ago. And beyond the horizon, beyond the edge of the observable universe, you see nothing at all because the light hasn't had time to reach you yet. And for some regions, it never will. This is distance in space. Not the simple separation we experience in everyday life, where you and I occupy the same moment even if we're in different cities. Cosmic distance is temporal as well as spatial. It disconnects observers in time as well as in space. It creates a universe where simultaneity is an illusion, where the present moment is purely local, where different regions exist in fundamentally different epochs from our point of view. And this has profound implications for what it means to be a living, conscious being in such a universe. Because if we're separated from most of the universe by billions of years of light travel time, then we're not just isolated in space, we're isolated in time. The present moment, the now we experience as we live our lives, is a tiny island in a vast ocean of past. When we look outward at the cosmos, we're not seeing our contemporaries. We're seeing history, archaeology, the cosmic equivalent of fossils and ancient ruins. And the future, which we imagine stretching ahead of us like a road we'll travel down, is not shared by distant regions. They have their own futures, disconnected from ours by the finite speed of light. Events that haven't happened yet from our perspective might have already occurred in distant galaxies, but we won't know for millions or billions of years. Events happening now on Earth won't be observable from distant galaxies until long after everyone we know is dust. This is the third illusion we need to confront and release: the comfortable assumption that space is a container where things exist simultaneously, where the universe is a single present moment that we can eventually map and understand and participate in as a unified whole. It's not. The universe is a vast collection of different moments, separated by distances that are fundamentally temporal as well as spatial. The present is local. Simultaneity is an illusion, and the further you look, the deeper into the past you see, until eventually you're looking at things that no longer exist, that transformed billions of years ago, that are separated from us not just by unimaginable distances, but by unimaginable spans of time. Understanding this changes everything about what distance in space really means. It's not just far, it's not just big. And the implications of that fact ripple outward into questions about exploration, communication, contact, and our place in a universe that isn't so much a place as it is a history book written in light. Let's bring everything together now. We've traveled through ideas that challenge the very foundations of how you thought about the cosmos. We've seen that cosmic distances are incomprehensible in scale, so vast that our brains physically cannot form meaningful pictures of them. We've seen that the units we use, those convenient measurements that seem so precise and scientific, actually create false impressions of understanding, making us think we grasp something we fundamentally cannot. And we've seen that distance in space is inseparable from time, creating a universe where everything we observe is a record of the past, where looking outward always means looking backward, where simultaneity is an illusion and the present moment is purely local. Now let's explore what all of this really means, not just for astronomy, not just for science, but for us, for humanity, for what it means to be conscious beings in a universe of such staggering scale and such profound isolation. Start with the most practical implication, one that might be difficult to accept. Interstellar travel is almost certainly impossible in any meaningful sense. Not just difficult, not just requiring technology we haven't invented yet, but fundamentally, practically, physically impossible given the scale of the distances involved and the laws of physics as we understand them. The nearest star system to our Sun is Proxima Centauri, 4.24 light-years away. That's approximately 25 trillion miles. The fastest spacecraft humanity has ever built, the Parker Solar Probe at its maximum velocity, would take roughly 6,300 years to cover that distance. The Voyager spacecraft, currently the most distant human-made objects, traveling at about 38,000 miles per hour, would require over 70,000 years to reach Proxima Centauri if they were pointed in that direction, which they're not. Even hypothetical future technologies face severe, perhaps insurmountable constraints. Imagine we could build a spacecraft capable of traveling at 10% of the speed of light. That's 18,600 miles per second, roughly 50 times faster than Voyager. Far beyond anything we can currently engineer or even seriously propose with existing physics. Such a spacecraft would still take more than 42 years to reach Proxima Centauri. 42 years, a human lifetime. You could be born, grow up, get educated, have a career, raise children, and grow old during that journey. And that's just one way. The round trip would take nearly a century. Any crew that departed would never see Earth again as they knew it. Everyone they loved would age and die while they traveled. They would return, if they returned at all, to a world transformed, where they were strangers, historical curiosities, relics of a past that had moved on without them. And the engineering challenges are staggering beyond current imagination. Accelerating a spacecraft to 10% of light speed requires enormous amounts of energy. The kinetic energy of a spacecraft traveling at that velocity is immense. For even a small probe weighing 1,000 kilograms, about the mass of a compact car, reaching 10% of light speed would require energy equivalent to millions of tons of conventional rocket fuel. The energy needed to accelerate a crewed spacecraft with life support systems, supplies for decades of travel, and equipment for whatever mission they're supposed to accomplish would exceed the total energy output of human civilization. Then there's the problem of cosmic radiation. At high velocities, the sparse hydrogen atoms and dust particles that drift through interstellar space become deadly projectiles. At 10% of light speed, each collision releases significant energy. Over decades of travel, the accumulated damage to any spacecraft, let alone human passengers, would be catastrophic. Shielding against this radiation adds mass, which requires more energy to accelerate, which creates more engineering problems, which add more mass, in a vicious cycle that may have no solution. And you can't just accelerate, you have to slow down when you arrive. That requires just as much energy as speeding up, meaning you need to carry your deceleration fuel with you, adding more mass, requiring more energy to accelerate, compounding the problem further. Some proposals try to sidestep these challenges with creative approaches. The Breakthrough Starshot Initiative proposes using enormous ground-based laser arrays to accelerate tiny spacecraft, weighing perhaps a gram each to perhaps 20% of light speed. These light sails would ride beams of focused light pushed by photon pressure rather than carrying fuel. At 20% of light speed, such a probe could reach Proxima Centauri in about 21 years. But these spacecraft would be tiny, smaller than your thumbnail. They couldn't carry humans. They probably couldn't even carry enough instruments to do meaningful science at the destination. They'd flash through the Proxima Centauri system at 20% of light speed, having perhaps hours or days of close observation before they'd traveled too far to send back useful data. And even those minimal signals would take over 4 years to reach Earth. The energy requirements for the laser array would be staggering, perhaps 100 gigawatts of focused power, sustained for minutes, aimed with precision across billions of miles. The engineering is so far beyond current capabilities that it might as well be magic. And even if it worked, we'd get a few snapshots from a probe too small to carry much instrumentation, decades after we launched it. For anything larger, anything that could meaningfully explore another star system or carry human beings, the energy requirements become absurd. To accelerate a crewed spacecraft to significant interstellar velocities would require more energy than humanity currently produces in years, perhaps decades, perhaps centuries. And remember, this is all just to reach the nearest star, one star out of hundreds of billions in our galaxy alone. The Milky Way is approximately 100,000 light years across. Even traveling at the speed of light, which physics prohibits for anything with mass, it would take 100,000 years to cross our galaxy from one side to the other. At 10% of light speed, that journey would take 1,000,000 years. At realistic spacecraft velocities, tens of millions of years. And the Milky Way is just one galaxy among an estimated 2 trillion in the observable universe. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light-years away. At light speed, the journey would take 2.5 million years. At any achievable velocity, longer than our species has existed. Longer, perhaps, than any species will ever exist. This means something profound that science fiction has trained us to ignore. Humanity is almost certainly confined to a tiny region of space, probably forever. We might, eventually, with enormous effort and resources beyond anything we've ever marshaled, send robotic probes to nearby stars. We might, over centuries of development, establish outposts in our own solar system, on the Moon, on Mars, perhaps in the asteroid belt or the moons of Jupiter and Saturn. These would be monumental achievements, transformative for our species. But interstellar empires, galactic civilizations, federations spanning thousands of star systems, humanity spreading across the cosmos like in the movies, These are fantasies. Beautiful dreams, perhaps, but fantasies nonetheless. The distances render them impossible, not impractical. Impossible. The universe doesn't care about our aspirations. The speed of light doesn't bend for our ambitions. The distances are what they are, and no amount of hoping or dreaming or technological advancement will shrink them. Some people find this conclusion distressing. We're explorers at heart. We're pattern-seeking, horizon-chasing creatures who dream of discovery, of new worlds, of going where no one has gone before. The idea that most of the universe is permanently, irrevocably beyond our reach conflicts with something deep in the human spirit. But there's another way to see this. A perspective that transforms limitation into meaning. Consider what it means that we exist at all. The universe is approximately 13.8 billion years old. For almost all of that immense span of time, there were no observers anywhere, as far as we know. No minds to wonder at the vastness of space. No consciousness to contemplate the meaning of distance. No beings to ask questions or seek answers. Stars burned through their nuclear fuel and died, collapsing into white dwarfs or neutron stars or black holes. Galaxies formed from primordial hydrogen, evolved through billions of years, collided and merged with other galaxies. Light traveled across billions of light years of void, carrying information about cosmic events, messages from the distant past, and none of it was witnessed. None of it was understood. The universe simply happened, event after event, with no one to appreciate what was occurring. Then, about 4.5 billion years ago, on a small rocky planet orbiting an unremarkable yellow dwarf star in an ordinary spiral galaxy, something extraordinary began. From the simple chemistry of early Earth, life emerged. Single cells at first, then, over billions of years of evolution, complexity grew. Multicellular organisms appeared. Nervous systems developed. Brains became larger and more sophisticated. And eventually, on this one small world, consciousness arose. Beings appeared who could look up at the night sky and wonder what they were seeing, who could measure distances and calculate speeds, who could understand that the points of light overhead were other suns, separated from us by light years of emptiness, who could grasp, however imperfectly, the scale of the cosmos and their own smallness within it, that you exist at all, that you're here right now reading these words and contemplating cosmic distances, is extraordinary. Not in some vague inspirational sense. Literally extraordinary. Exceptionally rare. Perhaps unique in all the universe, as far as we can currently determine. The universe has become aware of itself through you. Through beings like you. Through nervous systems that somehow learn to contemplate the very physics that created them. That's not nothing. That's not a trivial accident. That's remarkable. Perhaps the most remarkable thing that has ever happened in 13.8 billion years of cosmic history. And here's what the distances tell us once we understand them properly. They tell us something crucial about our situation. We're not central. We're not special in the sense that the universe revolves around us. We're one species on one planet, orbiting one star among hundreds of billions in one galaxy among trillions. The distances make this achingly clear. Earth is not the center of anything. The sun is not the center of anything. Even our galaxy occupies no privileged position. We're somewhere, just somewhere. A random location in a cosmos so vast that our particular coordinates are cosmically meaningless. The distances humble us. They show us that the universe is indifferent to human concerns, that it operates on scales that dwarf our entire existence, that everything we've ever done or will ever do occupies an infinitesimally small corner of space and time. But the distances also elevate us, because out of all that vastness, in all those trillions of galaxies and sextillions of stars spread across billions of light years of space, we know of exactly one place where consciousness exists. One place where beings ask questions about the nature of reality. One place where the distances are contemplated, the scale is appreciated, the meaning is sought. Here, Earth. This small blue world orbiting this ordinary star. Maybe there's life elsewhere. The universe is so vast, the number of potentially habitable worlds so large, that it seems improbable we're completely alone. Somewhere out there, orbiting some star we've never catalogued in some galaxy we've never named, there might be other minds looking up at their own night sky, wondering their own wondering, but we don't know. We've never detected a signal from another civilization. We've never found evidence of intelligence beyond Earth. Despite decades of searching, despite listening with radio telescopes pointed at thousands of stars, we've heard nothing but cosmic silence. As far as we can currently tell, we might be the only observers in the entire observable universe, the only place where the cosmos has developed the ability to understand itself. This silence, this apparent emptiness of intelligent life across the cosmos, has a name. Scientists call it the Fermi paradox. The physicist Enrico Fermi, contemplating the vastness of the universe and the billions of years it has existed, asked a simple question: where is everybody? If the universe is so large and so old, and if the conditions for life are not impossibly rare, then surely other civilizations should have arisen. Surely some of them should have developed technology. Surely, given millions or billions of years of head start, some of them should have found ways to make their presence known across interstellar distances. And yet we see nothing. We hear nothing. The universe appears empty of intelligence, or at least empty of intelligence that has made itself detectable to us. There are many possible explanations for this silence. Perhaps life is far rarer than we assume, requiring conditions so specific that Earth might be genuinely unique. Perhaps intelligent life is common, but technological civilization is not, with most species never developing the capacity to communicate across space. Perhaps civilizations inevitably destroy themselves before they can reach out to the stars, victims of their own technological power. Perhaps they exist, but have no interest in communication, or communicate in ways we cannot detect, or have reasons for remaining hidden that we cannot fathom. Or perhaps the distances themselves are the answer. Perhaps the gulfs between stars are so vast, and the time required to cross them so immense, that civilizations simply cannot make contact with each other. They rise and flourish and fall, each on their own isolated world, never knowing whether others exist, never receiving confirmation that they are not alone. The universe might be filled with life, filled with intelligence, filled with civilizations asking the same questions we ask, and yet each one might be permanently, irrevocably isolated by the sheer scale of cosmic distance. If that's true, it makes our situation both more tragic and more precious. We might be surrounded by kindred minds, fellow wanderers scattered across billions of light years, all of us looking up at the same stars, all of us asking the same questions, and none of us able to reach each other. The distances don't just separate us from empty space, they might separate us from countless civilizations that we will never know existed. This possibility should transform how we think about our own world. Consider what Earth represents in this context. If conscious life is rare, if technological civilization is rarer still, and if the distances between such civilizations are unbridgeable, then this small planet takes on an importance that transcends anything we normally consider. Every forest, every ocean, every ecosystem, every species that has evolved here over billions of years, all of it becomes cosmically significant. We're not just stewards of one planet among many potential homes. We might be stewards of the only place in billions of light years where complex life exists at all. The pale blue dot that Carl Sagan described, that tiny pixel of light in the vast darkness, isn't just our home. It might be the only home that consciousness has ever known in this entire region of the universe. Every war we fight, Every ecosystem we destroy, every species we drive to extinction, takes on a different weight when you consider that there might be no backup, no other Earth waiting to be discovered, no second chance on a distant world if we ruin this one. The distances teach us this. They show us that we cannot escape our problems by spreading to the stars. We cannot flee a damaged Earth and start over somewhere else. Whatever future humanity has, whatever future consciousness has on this planet, will unfold here, in this solar system, on this world, or perhaps eventually on neighboring worlds that we might terraform and settle over centuries of patient work. And that brings us to a different kind of hope. Not the hope of escaping to the stars, but the hope of building something meaningful within our reach. Our solar system, the one tiny bubble of space we might actually explore and inhabit, contains wonders enough for millennia of discovery. Mars, with its ancient river valleys and polar ice caps, might once have harbored life and might again if we bring it there. The moons of Jupiter, particularly Europa with its subsurface ocean, might contain life right now, swimming in dark waters beneath miles of ice, utterly unaware of the universe beyond. Titan, that strange moon of Saturn with its methane lakes and thick atmosphere, presents an alien landscape unlike anything else we know. The asteroids contain resources that could sustain human civilization for millions of years if we learn to access them. None of this requires faster than light travel. None of it requires technologies that violate physics. It requires only patience, dedication, and the wisdom to take a long view of human destiny. Within our solar system, we might build something extraordinary: permanent settlements on Mars, research stations on the moons of gas giants, mining operations in the asteroid belt. Perhaps eventually, over thousands of years, we might construct habitats that orbit the sun at various distances, each one home to communities of humans adapted to their particular environment. This would not be galactic civilization. It would not span light years. It would remain forever confined to the tiny region of space that our sun illuminates and warms. But it would be something. It would be the spreading of consciousness beyond a single fragile world. It would be the creation of a future in which humanity is no longer dependent on the health of one planet, one biosphere, one ecosystem. And all the while, even as we build within our solar system, we could continue to observe the universe beyond. We could build telescopes of unimaginable power, instruments capable of detecting the atmospheres of planets orbiting other stars, perhaps even detecting the chemical signatures of life or technology. We might never travel to those worlds, but we could know they exist. We could confirm that we are not alone, even if we can never shake hands with our cosmic neighbors. There is a strange comfort in this. The universe denies us travel but permits us observation. It keeps us confined to our small corner of space but allows us to see almost everything that exists. We are prisoners, in a sense, but prisoners with a window that looks out on infinity. We can know the cosmos even if we cannot walk through it. This is perhaps the most profound gift that the universe offers consciousness. Not the ability to go everywhere, but the ability to see everywhere. Not the power to touch the stars, but the power to understand them. The photons that arrive at our telescopes have traveled for billions of years, and they carry information about the entire history of the universe. We can reconstruct that history. We can understand the physics that governs it. We can know, with increasing precision, what the universe is, how it works, and how it came to be. No other phenomenon that we know of can do this. Rocks cannot contemplate the stars. Oceans cannot wonder about the Big Bang. Only minds, only consciousness, only beings like us can take the light that has traveled across the cosmos and transform it into understanding. If that's true, even partially true, even possibly true, it changes everything. It means this tiny planet, this pale blue dot orbiting an average star in an average galaxy, is not just our home, it's the home of cosmic self-awareness, the only island of consciousness in an ocean of empty space that extends for billions of light years in every direction. The distances take on entirely new meaning in this context. They're not just measurements, they're not just barriers to exploration, they're reminders of our isolation, of how rare and precious conscious experience might be, of how the vast majority of the universe, the overwhelming bulk of existence, is cold and dark and utterly devoid of anyone to appreciate it. And this brings us to perhaps the strangest implication of understanding cosmic distance. The universe exists whether or not anyone observes it. Stars burn through their hydrogen and helium regardless of whether any being watches them shine. Galaxies spin through their slow rotations whether or not minds comprehend their structure. Light travels through the void, carrying information about cosmic events, whether or not that light ever encounters an eye or an instrument to receive it. None of this requires consciousness. The physics works fine without observers. The universe would continue doing what it does even if no life had ever arisen anywhere, even if no mind had ever contemplated existence. But meaning, significance, understanding, these require minds. Without observers, the universe is just a series of events. Things happening according to physical laws, causes and effects unfolding mechanically, but nothing appreciating what's occurring, nothing finding it beautiful or terrifying or awe-inspiring, nothing asking why. When you contemplate the distances in space, when you try to wrap your mind around light years and parsecs and the billions of years that light has been traveling to reach your eye, you're doing something the universe cannot do for itself. You're making sense of it. You're finding patterns and relationships. You're creating meaning where otherwise there would be only events. The distances are vast and cold and utterly indifferent to your existence. The universe doesn't care that you're trying to understand it. The stars don't burn brighter because you're watching. The galaxies don't spin faster because you're contemplating them. But your contemplation matters anyway. It matters because it's rare. It matters because it might be unique. It matters because consciousness, wherever it arises, brings significance to what would otherwise be mere occurrence. This is what distance in space really means once you strip away the illusions and confront the reality directly. It's not just a barrier to exploration, though it is certainly that. The distances ensure that most of the universe is forever beyond our reach, that we'll never walk on planets orbiting other stars, that we'll never shake hands with beings from other worlds, that our cosmic neighborhood is effectively limited to this one solar system no matter how long our species survives. It's not just a reminder of our smallness, though it's that too. The distances show us that Earth is a mote of dust suspended in a sunbeam, as Carl Sagan famously said. They show us that all of human history has occurred on one tiny world in one corner of one galaxy, that everything we care about and fight over and dream about occupies an infinitesimally small portion of what exists. But distance in space is also a measure of how extraordinary consciousness is, how unlikely, how precious. In a universe of unimaginable scale, mostly empty vacuum, mostly cold, dark void, mostly devoid of anything that thinks or feels or wonders, you exist, you think, you feel, you wonder. The light from distant galaxies has been traveling for billions of years, photons that left those galaxies when the universe was young, when Earth didn't exist, when the atoms that would eventually become your body were scattered across light years of interstellar space. That light has been crossing the void ever since, passing through emptiness so profound that your mind cannot picture it, surviving the journey across billions of years of cosmic time. And tonight, that ancient light reaches Earth. It enters our atmosphere. It passes through the lens of a telescope or perhaps just the lens of your eye. It triggers chemical reactions in your retina. It creates electrical signals that travel to your brain. And somehow, through processes we still don't fully understand, you become aware of what that light represents. You understand that you're seeing the distant past. You grasp that you're connected across unimaginable distances and spans of time to events that occurred before your world existed. Something remarkable happens in that moment. A connection is made across billions of light years. Information that has been traveling since before Earth formed finally reaches a mind capable of understanding it. Through your wondering, the cosmos gains meaning it could never have alone. When you look up at the night sky on a clear evening and see the Milky Way stretching overhead in a band of diffuse light, you're seeing hundreds of billions of stars. Most are thousands or tens of thousands of light years away. The light reaching your eye tonight left those stars when human civilizations were young, when the pyramids were new, when history was just beginning. Some of that light left before humans existed at all, when our ancestors were still apes in African forests, when no being on Earth looked up and wondered what those lights might be. That light has crossed the void, passing through the emptiness between stars, carrying information about distant suns and the worlds that might orbit them. It has traveled through space where nothing exists, where the vacuum is more perfect than anything we can create in laboratories, where loneliness extends in every direction for trillions of miles. And you're the one who receives it. You're the endpoint of a journey that started before you were born, before your civilization existed, perhaps before your species evolved. The photons that enter your eye tonight have traveled distances that defeat comprehension, survived the trip across the cosmos. And now, finally, after their long journey through the dark, they've found an observer who can appreciate what they represent. This is the experience of distance in space, when you truly understand it. Not just numbers and measurements, though those are part of it. Not just barriers and limitations, though those are real and permanent. But also connection, wonder, meaning created by conscious beings in a universe that seems almost designed to prevent exactly that. The distances are real. They're vast beyond comprehension, beyond intuition, beyond any mental picture you might try to form. They limit what we can explore, what we can know, what we can physically reach. They separate us from most of what exists, probably forever, creating a cosmic isolation that no technology is likely to overcome. But the distances also create perspective. They show us where we stand in the cosmic order. They humble us by revealing our smallness and elevate us by demonstrating our rarity. They remind us that existence is not something to take for granted. That consciousness, wherever it arises in the universe, is a precious and improbable thing. Distance in space doesn't mean what you thought it meant before tonight. It's not just big numbers that are hard to visualize. It's not just abstract measurements that astronomers use in their equations. It's not just barriers that might someday be overcome with better technology. Distance in space is the context of our existence, the framework within which our brief lives occur, the scale against which our achievements and failures are measured. The void that makes consciousness meaningful by contrasting it with so much emptiness, so much darkness, so much cold and silent nothing. When you look up at the stars tonight, you'll see them differently than you did before. Not just as points of light, decorations on the dome of the sky, but as distant suns, separated from you by light years of empty space. You'll know that the light reaching your eye has traveled for years or decades or centuries or millennia. You'll understand that you're looking into the past, seeing the universe as it was long before you were born, receiving messages that were sent before human civilization existed. And you'll realize that you, standing on this small planet, looking up at those impossibly distant stars, are part of something extraordinary. Distance is being contemplated, scale being appreciated, meaning being made in the void. That's what distance in space really means when you strip away the illusions and confront the truth. Not just separation, but significance. Not just isolation, but illumination. Not just the vast and empty darkness stretching away in every direction, but the small points of light within it, stars burning in the void, and minds reaching out to understand them. The light from the most distant galaxies has been traveling for more than 13 billion years. It carries information about a universe in its infancy, stars that no longer exist, galaxies that have long since transformed beyond recognition, light from an era when Earth didn't exist, when the sun hadn't ignited, when the atoms that would someday become you were scattered across light years of primordial gas clouds. That light finally arrives here, on this small planet, where beings with curious minds point telescopes at the sky and ask the questions that matter. What does it mean? How far? How old? How vast? Why? Distance in space is the question. And you, with your consciousness and your wonder and your relentless need to understand, are part of the answer. The universe is enormous beyond comprehension. The distances defeat our intuition and humble our aspirations. The units we use create illusions of understanding that mask a reality too vast to truly grasp. The separation between us and everything else is measured not just in miles, but in years, not just in space, but in time. But we try to understand anyway. We measure, we calculate, we build analogies and scale models that inevitably fail. We point telescopes at the sky and push the limits of what can be observed. We ask questions that may have no answers and seek understanding that may forever elude our complete grasp. And in that reaching, in that striving, in that refusal to accept our cosmic isolation without at least trying to comprehend it, we find something extraordinary, not because the universe cares, not because our efforts change the distances or bridge the gaps, but because the effort itself is meaningful. Because consciousness, wherever it exists in this vast and mostly empty cosmos, illuminates the darkness. Because minds that wonder are precious beyond measure in a universe that mostly just is. Distance in space doesn't mean what you thought. It's not just far, it's not just big, it's not just hard to reach. It's the measure of our isolation and the context of our existence. It's the framework that makes consciousness meaningful by showing how rare consciousness might be. It's the question that humanity keeps asking even when the answers seem impossibly out of reach. And tonight, when you step outside and look up at the stars, you'll understand what you're really seeing. Ancient light from distant suns, windows into the past scattered across the dome of the sky, evidence of a universe so vast that your mind cannot truly picture it, cannot truly grasp it, cannot truly hold it. But you'll try anyway, because that's what conscious beings do. We reach for understanding even when understanding is impossible. We ask questions even when answers elude us. We look up at the stars and wonder, even when the stars are separated from us by light years of void, by barriers of time as well as space, by distances that mock our aspirations even as they inspire our curiosity. That's what it means to be human in a universe of such scale. To be small and to know you're small. To be isolated and to feel that isolation. To be limited and to push against those limits anyway. The distances are real, they're vast, they're probably permanent barriers that no future technology will overcome. But you're here, right now, thinking about them. And in that thinking, in that wondering, in that ancient human act of looking up at the night sky and asking what it all means, you're participating in something remarkable. And that's what distance in space really means. Not just the space between things, but the space that makes consciousness precious by showing how much emptiness surrounds it. Not just the time light takes to travel, but the time that connects us to the distant past every time we look up. Not just separation, but the kind of separation that makes connection meaningful when it occurs. Thank you for joining me on this journey through the cosmos and our understanding of it. If you found value in this exploration, please consider liking this video and subscribing. Your support helps me continue making these deep dives into the nature of our universe. And remember, the next time someone tells you a star is 4 light years away, you'll know what they're really saying. They're describing a gulf so vast that light itself, the fastest thing in the universe, needs years to cross it. They're describing a separation in time as much as space. They're describing a universe where distance doesn't just measure how far things are. It measures everything about what it means to exist in a cosmos of this scale. Good night, and may you never look at the stars the same way again.